Hello, everyone. Welcome to our webinar today. We will get started promptly at the top of the hour here. Welcome to everyone who's just joining us. We're going to get started in just a couple moments. Perfect. I do have the top of the hour, so we are ready to get started. Good morning, afternoon to everyone, and welcome to today's AEESP webinar supported by Sustaining Member Regenesis, In Situ PFAS Remediation, out of the lab and into the ground with viable technologies. I know that we are all eager to get started with today's presentation, but I just have a couple of quick housekeeping items before we do. On the slide in front of you, you are able to see how to contact your hosts and panelists, as well as ask questions. We will be taking all questions today at the end of the webinar. That being said, please feel free to ask your questions at any time during the session using that Q&A toolbar located in the bottom of your webinar browser. You'll be able to see that demonstrated on the slide. And just a reminder that you will all receive the webinar recording and slide deck by the end of this week after today's session. So thank you again to AEESP Sustaining Member Regenesis. And without any further ado, I will hand things over to our moderator, AEESP President, Cara Nelson. Cara, please take it away.
Thank you, Erica. So I'd like to begin by adding my welcome to everyone. Thank you so much for joining us today. As Erica said, my name is Cara Nelson. I'm a professor at UC Berkeley in environmental engineering, and it is my great honor to be the president of the Association of Environmental Engineering and Science Professors this year. And this is our very first Sustaining Member webinar. This is a new program that we believe will be of great benefit to our members and our broader community. And these webinars are free to attend, and you do not need to be an AEESP member. So when you receive an invitation to one, feel free to share them beyond the AEESP community. And if you are not familiar with AEESP, we are a diverse and inclusive community of over 1,400 members. Our members include educators, researchers, graduate students, and we also have a special category for companies and organizations who can join as sustaining members. So Regenesis is one of our sustaining members. I want to emphasize this is an organization that is run by volunteers, and you can be one of those. So I want to encourage you, if you're not already a member, to consider joining and volunteering to be on one of our committees or task forces. We have a wide range of activities and programs that support the professional development of our members, and our organization aims to also evolve our field to make sure that we are addressing the grand challenges, not just of today, but of the future. So if you would like to learn more, please go to our website, which is aeesp.org. You can also look for us on LinkedIn, and you are also welcome to shoot me an email, and you can find my email address on our website. So now it's my pleasure to introduce our speaker today, Dr. Paul Erickson. He is the Vice President of Research and Development at Regenesis Remediation Solutions, and he has been with Regenesis for a little over 8 years. Prior to that, he was at ETH Zurich in Switzerland for almost 8 years, where he completed his PhD as well as a postdoc, and then continued as a senior scientist in the lab of Professor Chris McNeil. And fun fact, we met when I was at ETH Zurich just a little over 10 years ago on sabbatical. So it's really fun to be here together in this entirely new format with you, Paul. Um, as Erica said, we're gonna save answering and discussion until the very end of the presentation. So once Paul gets started, please submit any questions that you have into the Q&A panel. And once he finishes his presentation, I will be moderating the Q&A sessions, and we're looking forward to that. So super happy to have you all here. And with that, I will hand things over to Dr. Erickson.
Yeah, thanks a lot, Cara, for the introduction, and Erica for as well. In your intro kind of me and my academic background, I'll come right out of the gate and remind the graduate students out there that what you're doing right now doesn't necessarily have to be involved with what you then do in the future. So back when Cara and I met, when I was at ETH Zurich working for Chris McNeil, I studied photochemistry, and everything that I'm going to tell you about today is devoid of light at all. We're going to be down in the groundwater, and as the title of my talk suggests, looking at ways that we can manage PFAS impacts in the groundwater. And so with that, I will jump into the talk here. So a quick overview. For those that aren't so familiar with groundwater remediation, the industry, I'll kind of paint the picture about what we do at Regenesis and how it fits into the remediation, call it landscape, and also try, again, for those that aren't so familiar with how the industry works, where does a company like Regenesis sit? Where do those that have contaminated sites that are in need of management sit? And then relevant to the topic, the theme that I'd like to run through this talk today is how do partnerships with academic groups kind of help push things forward and help produce data and good science that benefits everyone. And so, I'll jump into in situ remediation specifically to PFAS, give a quick overview of mechanisms of migration pathways of PFAS in the environment. And then really the core of my talk today will be about a in situ field application, a research project that was funded by the Navy that looks at one particular technology that Regenesis has, and that's using in situ, using activated carbon, colloidal activated carbon, to help manage PFAS impacts in groundwater. And then with that, I'll kind of close with some highlights on, again, academic work that's been done and ongoing to help increase the understanding of methods like this, improve how we use them, and understand where they're best applied, when and how. And so, as I said, I'll just, again, for those that aren't so familiar, try to paint the picture about in situ remediation, what it looks like, and what we do at Regenesis. And so, first off, the most common contaminants that we deal with, by far not an exhaustive list, but starting from the top, petroleum impacts are something that the in situ remediation world really started with. So corner gas stations had tanks that were notoriously leaky, and that's still to this day one of the main things that companies like Regenesis and are involved in cleaning up is petroleum impacts. Chlorinated solvents, whether that's from dry cleaners or industrial sites, and then PFAS, the contaminant of our careers, those of us that are in this world now. The way that we go about addressing these contaminants in the environment, you really, or in groundwater specifically, you kind of can boil things down into two different strategies. And one is a method that you then remove the contaminated groundwater by pumping it to the surface. Then you can first, oftentimes you have to concentrate up that whatever the contaminant is. Then there's transport, storage, disposal. But you've got the contaminants there. You can do something with them after you've pumped them. That has some of its own challenges that I'll touch on later. But what we work on and what we focus on in Regenesis are these in situ methods, where we're going to inject some amendment, something in the ground that's going to then passively help remediate or manage the contaminant that we're dealing with. So some of the different strategies that we offer at Regenesis and others, different technologies, can be something like bioremediation, where we are using bacteria to break down contaminants. Abiotic, so that could be chemical oxidation or reduction, as a picture I show here, where you can use zero-valent iron to treat chlorinated solvents. But what I'll talk about today are these retention-based technologies. So using adsorbent, colloidal activated carbon, you can see a picture of it here, where we can inject these materials that are sorbents and use them, in the case that I'll talk about, to manage PFAS impacts in groundwater. So again, I mentioned that I just set up the stage on where does a company like Regenesis fit in the world of remediation. And so this is what you've got. This is kind of the different groups that are at play here that we'll talk about. So site owners are those that they've got contaminated land or an issue that they're dealing with. Usually they're talking to a consultant directly. This isn't a perfect map. Obviously, there's crossover on a lot of these fronts, but just giving you an idea of how Regenesis, a tech development company, sits in the world. And so everyone's got different questions that they're trying to address and problems that they're trying to solve here. And so as a site owner, what do I have to do? What's required of me, whether that's by regulation, what have you. But they're working with a consultant that's helping them figure out, what, based on what you have to do, what's feasible, what's going to be cost effective. They're kind of helping put together the different technologies that they come to companies like Regenesis, which we've got our own set of issues and challenges that we're trying to overcome. Once we have a technology, how are we going to manufacture this? How are you going to get it to scale? We need to write technical operating procedures when you have these technologies and be the experts on getting them into the ground. And that's really where the partnership with academics comes in. And so, we don't have the resources or the brain trust that you can find in academia, whether that's from initial concepts that may be a good idea, but it's not clear exactly how we're going to package this into something that is able to be brought to the field, is cost effective, all the things that it requires to get it onto an actual site and worked on. That's where the partnerships, that's where the connections with between an academic group and a technology development company like Regenesis really come through. Is we don't have the same instrument resources, we don't ask the same questions. So really, what I'll try to do is through this talk point out some instances where, whether it's different strategies to make measurements related to our technologies, or questions that come up about the effectiveness of the technologies and how they'll evolve with time. That's really where the academic partnerships that we lean on are really useful, with the end goal to bring viable commercial solutions. So get something out of the lab and get it into the ground in a way that that can be put into practice and solve some of these very real issues that are out there in the environment. And so I show this picture for a couple of reasons. One, to highlight when you've developed something, especially an in situ technology, where it's kind of understood that it's got flexibility. I can pick this up and hopefully bring it anywhere. And that's what I'm trying to highlight here. But on a personal note, you end up going to lots of different locations, and that's one of the things about the job that I really like. And so this picture here on the left is an installation locally of a passive flux technology that we've onboarded because, and I'll touch on this in the talk, it's a really valuable way that we find to collect groundwater mass flux data. Well, we were trialing this in a local office here in California, which is where I'm based out of now. This is a picture of an early beta project that I worked on in my home state, which is Florida, actually, North Florida. And then this is a project site where we're working in someone's basically front yard, in Switzerland, which we also do work in, and as Cara pointed out, where I did a lot of my graduate work. So the idea is that these technologies, they can wind up anywhere. You got to be able to pick them up and take them just about anywhere. And again, academics are how we answer those detailed questions to let someone like a tech development company figure out the specifics on how are we going to move this around and get it applied. So with that, now I'll jump into PFAS. So again, that was the contaminant that most of us spend a lot of time thinking about and working on in the industry now. And I'll start with a PFAS family tree. And so, we know that there's quite a few different PFAS when you draw the circle around it. And what I'd like to do is try to capture here with this figure out of this publication by Chuck Newell and others at GSI. You've got all the way on the left here, PFAS polymers. So not really environmentally concerned because they don't move around so much. That may not be the full story, but generally speaking, once we're talking about groundwater, you're looking for things that are the most mobile or the most concerning from bioaccumulation and health concerns. And so the way that I show people this slide is, these are your precursors. These are the polyfluorinated contaminant PFAS that can get transformed into our environmentally persistent perfluorinated compounds. And so from an environmental concern standpoint, at least from the regulation standpoint, the importance kind of goes from left to right, kind of ending with the two that have the most attention, by far not the end of the story, but PFOS and PFOA, which you can see here. And so how do they get into the environment? How do they move around? I'll touch on that. And what are the problems that are specific to groundwater with PFAS? And so you can see here in this diagram that the releases are pretty diverse. So what I'll focus a lot on today is the PFAS that are resulting from and as a part of AFFF, so aqueous film forming foams releases. This was a direct release to the environment. One of the reasons why they're so important from a groundwater impact standpoint, but again, far from the only one. Industrial point sources, so industry produced and used a lot of PFAS. And then there's the more relevant to our day-to-day lives, septic release. PFAS are present in all sorts of consumer products. And then resulting as well in wastewater treatment effluent releases to surface water. Another big one that many of you are likely familiar with that I won't talk about today is land application of biosolids coming from wastewater treatment plants, which have certainly contributed to groundwater impacts, but less of really at least the case study that I'll focus on. But you've got all these different releases to PFAS, whether that's to the air, soil, but eventually they make it to the groundwater, and you wind up with these long plumes that there's no real degradation in the environment, at least for perfluorinated PFAS compounds. So we can't lean on those other technologies that a company like Regenesis already uses, which is bioremediation. No proven application of bioremediation for PFAS. Very little good information or good data right now that there's in situ means of destruction for PFAS. And so we're kind of left with not very many options to try to reach these low targets for these extensive groundwater plumes that we get. And so really what you're left with is we've got these mobile contaminants, PFAS in the groundwater, and they're sort of finding their way into all these different places through the transport and retention mechanisms that are at play. So you can get a lot of PFAS that build up at air-water interfaces, not to mention that in the vadozone, they're on their way down. They're migrating through vadozones because a lot of times, especially in the AFFF impacted sites, they were applied directly to ground surface. So we got these long plumes where we've got partitioning into soil organic matter, air-water interface. I point out, and I'll talk a little bit more about this matrix diffusion. If you aren't familiar with this term, in groundwater, you've got sandy layers and you've got more low permeability clay-like layers. And matrix diffusion is this idea that with time, your contaminants will migrate into the water that fills these clay layers. And then even if you clean up the sand, you're going to get rebound from these contaminants that have made their way, not necessarily from partitioning, but really just diffusion into these zones. It's a little bit of both, but the point really is that even if you flush out these zones, it takes a significant amount of time to restore your aquifers, to get clean groundwater. So, and to give you a picture of just what we're looking at with PFAS and how it stacks up with some of these contaminants that we've dealt with in the past, because you get basically no degradation in the environment for your perfluorinated compounds, your PFAS, your plumes can be very long. And so starting down here on, these gas station related, these hydrocarbon related contaminants, BTEX and NTBE, there's plentiful microbes in the environment that can degrade even under anaerobic conditions when there's no oxygen. And so that tends to really, keep the size of these plumes oftentimes in check. And then as you go up to something like chloride, which is essentially a tracer, also no degradation of chloride. And so they start to look like these PFAS plumes. They get very long, very difficult to manage, and you have very few options. So we unfortunately find ourselves in a situation where you've got to potentially prioritize risk reduction over removal. We've got now there's tens of thousands of sites in the U.S. alone that have PFAS impacts in the groundwater. So we're going to need different strategies, different ways of thinking to deal with these contaminants once they've been released. So one idea, and really it forms the rationale behind the treatment that I'll talk about using colloidal carbon and injecting it into aquifers to increase the retention of PFAS within these areas is based on this concept of monitored natural attenuation. And so, it's not a do nothing strategy, but it's a focused risk reduction strategy is what it is. And so the idea goes something like this, that if you've got PFAS impacts in your groundwater, and they're then migrating on somewhere, what you're trying to do is prioritize and take note of where they're going and what they might be affecting. And then when you can, and when you need to, do something to try to alleviate when this mass shows up as a function of time. So we can add sorbents or just understand what the impacts will be to receptors. And I'll show some slides here in a second to get into what that means. But if you can take what would be without any retention, without any, whether that's natural retention, this matrix diffusion or these sorbents that we put in, but if you can add something to the problem or the situation and know that you can lower the discharge with time, then you're able to bring down what will show up in terms of mass as a function of time into an acceptable area, more manageable area. And so the idea that Adamson here is, again, the folks at GSI have painted is, it's this landscape kind of looks like a baseball diamond here, but if you've got PFAS plumes that are migrating, there's some mass discharge with time. And then on the y-axis here, you've got how close you are to a sensitive receptor. So drinking water wells or water bodies. And so what you're trying to do is understand where, higher being much higher discharge and then a shorter travel time being a problem because you're going to have an effect sooner. You can prioritize where these areas are. And if they're, low total mass and there's a long distance until you're going to impact the sensitive receptor, you may be okay to just monitor the contaminants and just understand and mitigate the impacts that way. And then when you've got when there's a situation where you've got more discharge or a closer receptor, you can put sorbents, you can do something. Sorbents is just one of the measures that they talk about, and the one that I'll talk about. But there's some things that you can do to try to push your problem, your site into this category that you can manage it in situ and save then the higher intensity, more expensive street treatment strategies for the situations that they really require. Because pump and treat, you will have situations where you still absolutely need to take the mass out of the situation or contain it by more intensive means. And so that's sort of the concept, the landscape behind using strategies like this. And so now I'll get into the case study here where this was a study that was done by Paul Hatzinger and his colleagues at Aptum, along with Tony Danko with NAFAC. And I present this case study. This is a technology that we've now used on a number of sites worldwide. But this is a good case study that kind of walks through the different steps to understand the technology, how you get it into the ground, the effectiveness of it within a limited time period, and then looking at some of the other impacts to an aquifer that you need to consider when you're injecting a solid, which colloidal carbon is still a solid. You got to keep tabs on other facts like hydraulic conductivity changes that may happen. And so these were the questions that the study we're trying to address. And so this is what it looks like. So you've got your PFAS plume, and then groundwater is pulling it into this area that we're going to treat with this colloidal activated carbon. And then you should get, if everything is working right, good distribution of your contaminants, and then removal by absorption and sequestration within this zone that we've performed our treatment. And so the tasks of this study were first assess the site that the treatment's going to be done on. They did some column tests, kind of as an assessment in the field or in the laboratory of just the basics of the idea. And then really I'll get into the results from there. I'll show some pictures of the installation and then walk through the results of the study. And so this is what the site looked like. It was, you can see here, a fairly sandy site. Depth to a confining layer, a clay layer, was about 25 feet. And so I'll show some data from this A to A prime. The demo area, you can see here in this yellow circle, is pretty close to soil boring 1. And so this was a fire training area. And you'll see in these data, so close over to where the demo area was, there was still quite a lot of PFAS in the upper borings, the groundwater in the upper areas. You can see it's dominated by these C8 PFAS, so PFOA and PFOS were really the most prevalent PFAS. You can see they're especially closer up towards the demo area and the source. There were still some of the precursors and other smaller chain PFAS, but it's as you get farther away, you can see that there's either by flushing or by diving the contaminations really in towards the bottom. But up in the area that we're working, there's a lot of mass still present up in the vadose. That'll come into importance when I show some of the results getting towards the end. Just a quick look at the column study. And again, this was kind of a go, no-go step in the process again, this was all work done in Paul Hatzinger's lab at Aptum. And it was try to ramp up the flow rate of the groundwater. So using site groundwater, site soil, they applied some of our plume stop colloidal activated carbon to the column, and then try to simulate in a series of just 4 months, 2.5 years, the study length of groundwater flow. So you can see here the evenness that the carbon is coating. They're going to pull the cores apart and confirm that here in a minute, but you can see it flowing on. So it just flows into the sands, and this is how you're able to build these hopefully continuous areas where you've put the sorbent that's able to remove the contaminant mass as your PFAS mass as it moves through. So just a quick, I'm really just going to move through this pretty quickly, but as expected, in a short duration study like this, you see complete removal of the PFAS in the treated column. So versus the untreated column where with very little lag, you see breakthrough. Again, that was because it was using site soil and site groundwater. But again, this is just a go, no go look at the performance of this approach. And then wanting to understand, okay, if we take this to the field, are we going to see distribution? Because we preferably like to have wide coverage of this sorbent so that you can remove the contaminants that are fluxing through and reach the sorb mass that's already present within the treatment area as well. So one way that they went about doing this is a combustion technique. So they segmented the column. You can see here it was frozen and segmented, and then tried to get the carbon that was in the soil column this way. You can see fairly even distribution, and by this method, they were getting about 5 grams of carbon per kilogram soil, so a little bit higher than expected. And then they tried another method, which was developed in part by, or really entirely by Ian Pham and his group at University of Waterloo. And it was a dye-based method that they got the idea for this, and we've spent some time back and forth with them on this because this is something that we can take to the field and use to help verify placement of our during an actual application. So this is an example of something that an academic group helping us develop tools that are very practical, have very strong relevance once you get to the field. And this is the demonstration of this being done in Paul's lab. But took that those same soils and then ran the analysis again. And you can see column 2 is the control, no carbon put on. Column 1 was the treated column, and got closer to what we expected and what you'll see the target dose was in the field, using this kind of method to figure out what the weight percentage is of our carbon on the soils. So this is what the demo area looked like, and you can see here we've got background wells to measure what the groundwater concentration for our PFAS is as they're moving into the treatment area. You can see here in the dotted line, I'll just drop this in. We use 12 injection points for the products, kind of targeting this depth you see here. So just above where the groundwater level is, which is denoted here, and then into this silty clay sand. The target dose on the soils within this treatment barrier was 2,000 milligrams of carbon per kilogram soil. And so that's what we're hoping to put in. That's what the dose is. And so then again, as contaminated water moves through, we should have absorption of our PFAS onto the carbon. And then we've got wells, you can see here, both at shallow and deep intervals that will look at the data from that was followed for the performance. Mainly what I'll focus on, and I've got a legend here that I'll show you once we get to some mass flux data. You'll see this is the up gradient wells, this is the barrier edge wells that I'll talk about, and then this is the 10 feet down gradient wells, and again, both shallow and deep for the data that we'll look at. Just to give you a picture of what it looks like to implement this in the field, and on this particular site, the water from the hydrants on the site, so this was in the Northeast, it was a naval air station in the Northeast, water had to be brought in and treated so that it didn't have PFAS in it. That was the request for the study. And then you can see a picture of the trailer where the products are mixed and then injected into the field through these temporary push rods. So I've shown already a couple of pictures of these geoprobes. So this is what we use in instead of dedicated injection wells. You can put in these temporary points where you can inject in the products after you mix them, and pull up the rods when you're ready to do different intervals. So there's a lot of flexibility on how you get the amendments in the ground and where you can work with tools like this if the geology will let you do it. So getting into the performance monitoring. So the field parameters that were measured, you can see here. But what I'll really focus on is the PFAS results, and then I'll show you some of the soil cores. Using those methods that were validated in the column study, they were able to go back out and, as a part of this project, look and understand the distribution of the carbon within the soil, within the treatment area as a part of the project. And then what I'll end with on the data is a measure of passive flux meters. And this is a tool that when you're talking about managing, mass discharge and, how much contaminants are leaving a site, it's important to think about mass flux. So how much of the contaminant, not necessarily in the concentration, but, what's the actual mass that's coming off of a contaminated area. And are you managing that properly? These passive methods are really important, really valuable for measuring that, as well as I'll touch on it, the impacts to the permeability of our area. So are we inhibiting groundwater flow with methods like this? So first, to look at the soil cores, and what you can see is that if you look at the pictures here, they're jet black within the treatment area. So they were taken right within where the injections were, right at the edge of the barrier, and quite black. You can also see some heterogeneity, and that's what you see in the data. So if you look at the background cores, this was done by the combustion method, so they weren't ready to use the dye method on this particular project. And so what you see is that there is a background organic carbon that's picked up on, or just volatilization of what's in the soils with this method in background. And so in these sandier soils, it's not so high, the background's not so high, there's not so much organic carbon. But in the silty clay soils, you did have quite a high background. And so we can subtract that out to get a measure of what the carbon concentration in the cores was compared to the background after application. And what you can see is kind of what you expect. So when we do these injections and put the carbon in the ground, what we're trying to achieve is a nice, even, uniform coating, but you do see heterogeneity in where the carbon goes. And that's expected. Your aquifers are quite heterogeneous, and your material is going to follow the path of least resistance when you inject it. And so that's generally what you see is you see distribution of these amendments, carbon or any amendment, within the areas that are more transmissive. But importantly, the dose that we got, the average dose within these cores, remember we said we were targeting roughly 2,000 milligrams per kilogram. Within these cores, we're in that ballpark, on average. So we got the material where we needed it to be. So now going into the data, this was 2 years of monitoring that are available for this project. And what I'll do is I'll step from up gradient to down gradient to give you an idea of what the performance has been like in this treatment. And so what you see is that 20 feet up gradient, this red line, you've got the shallow concentration. So this is total PFAS. And then the blue one here is the deep. And what you see is that you've got quite a lot of variability in the PFAS concentration. I mean, they vary by more than a factor of 2. And, working up close to the source area, like we said that we were, you've got ongoing infiltration potentially. And not to mention, you've got this air-water interface where you've got quite a lot of PFAS that tend to accumulate. And then if you have water table fluctuations, you can get mobilization of this mass down into the groundwater. And that's what you see here. So you've got the water table elevation. And what everyone kind of hypothesizes is that after you get these rainfall events where the water table comes up, you see these big fluctuations in your contaminant, your PFAS concentrations. That's much more attenuated in the deep, as you would expect. It's not as hydraulically connected with what you're seeing above. And so within the barrier edge, so what was the performance like? And for total PFAS, this is what we expected, is that both in the shallow and the deep, you get essentially immediate drops in your PFAS concentrations, a little bit of uptick here over time, and I'll get into what that is. And you can see here that really that was PFBA, which is breaking through. Because if we look at PFOA here and PFOS, at the barrier edge where you've influenced the aquifer directly with our amendments, you get basically knockout removal of these, fairly hydrophobic, relatively hydrophobic PFAS, your PFO and your PFOS. But what you do see is you see breakthrough of your shorter chain species. So this is one of the limitations of the technology. For the contaminants that are of most concern and most highest regulation right now, you get good removal and good performance. But for lighter chain species, this approach is in the same situation as many others, that these compounds, PFBA and short chains, they're too hydrophilic. They don't absorb well to activated carbon, and so we don't see performance with these species. They almost act for something like PFBA like a conservative tracer. If we move 10 feet down gradient, the story is quite similar. And I'll get into some of the nuance here, is that both in the shallow and the deep, there's a little bit of a lag in terms of when you see your drops in your concentration, and then there's some upticks. And again, this is most likely due to infiltration within that area that we see in the shallow, but performance is still good. It's on par with what was expected. And in the deep, you're more shielded from what's going on above and coming down from the vadose, and so the jumps aren't quite as dramatic. But that's again what you see both for PFOA, PFOS. There's this lag in the drop in the concentration, and that's because the groundwater that's within that barrier has got to reach that area 10 feet down gradient before you see the response and drops in the concentration. That's not the full story, but that's most of it. I'll get a little bit more into that here in a moment. But again, PFBA comes up as expected. It's not retained by the activated carbon. PFPEA, similar story, performance generally, but then we're starting to see what is most likely in the shallow area, infiltration from above or just picking up mass from this fluctuation in the water table. So another measure beyond concentration, as I mentioned, is mass flux. And so they use these devices. There's a few different offerings for this type of data collection, but the idea is that you can put in these resins that are going to accumulate the mass that's moving through onto these cartridges. And we're going to put them in each of our wells at a couple of different time points to figure out not just concentration, but what's the mass flux, and also what's the groundwater velocity. How is that varying from before and after we do our treatment? And just an example data plot to give you an idea of what kind of the power of these sorts of data approaches is on the top here, you've got Darcy velocity, and then on the bottom, this is mass flux. This is just an example plot, but by depth, you're able to delineate where's your groundwater moving. And in this plot, you see that it's fairly homogeneous. You don't have much change in your groundwater flow. But on this particular site, again, this is not the one that I'm presenting on, just a demo site. Sometimes you get one particular zone that's very important for managing, for really knowing where your plume is evolving from and being transported from. And sometimes it can be this very narrow zone. And for these injectable methods or any type of in situ work, understanding where your migration specifically is very important for doing it properly and getting the performance that you're after. So moving on to the data, you've got groundwater flow rates here, and you can see that, from baseline to year 1 and 2, there was quite a bit of variability, and this is due to the water table fluctuating. So as the groundwater table comes up, your groundwater velocity can go up or go down as well as a function of that. And so looking across the years and the different wells, both the backgrounds within the barrier and down gradient, there was no evidence of barrier clogging. So again, you do expect some modification to the permeability. You are putting adsorbent, but the loadings that we target, we do it with in mind to try to not change the permeability all that much. And then getting into the mass flux, the barrier, up gradient of the barrier, we saw again fluctuation. So from baseline to year 1 and 2. It's kind of all over the map. And again, this is partly because of the fluctuating groundwater. That was the shallow, same thing in the deep. And you can see here, this is now a log plot on our mass. So it's milligrams per meter square per day. So up gradient, that was the data. Once we get into the barrier, similar to the concentrations as you would expect, you see reductions, removal of your longer chain species is more or less complete. Again, PFBA, here's that mass flux upticking after even a year, and then of course the second year as well. And then deep, same story. Short chains are where you see a little bit of mass coming through, and then the longer chains, good performance. And then 10 feet down gradient, that same, for at least PFOS, that same trend that we saw where you've got a decrease from year 1 and 2, especially over baseline. You see that in the mass flux data. And then same story in the deep sections as well. And so kind of wrapping up the case study here, what we were seeing in the shallow was very likely due to this water table coming up and down. you've got PFAS that end up getting mobilized, and you can see that in the shallow. So that's something that has to be accounted for when you're designing these treatments and deploying them. Is what's your performance metric, and what's your expectations on what you're able to achieve with methods like this. In the deep, the mass that we likely saw in these down gradient wells, not so much in the barrier wells, was likely due from this matrix back diffusion, where contaminant mass that's been loaded up over the years in these silty areas, that's coming back out, and you start to see that especially down gradient. So just project summary, overall the project conclusions were that this type of approach and others like this, using colloidal carbon, it's a means to get this enhanced retention of PFAS. You can manage mass flux as an interim measure, and depending on the situation, it can be an important strategy in how you're managing PFAS impacts in groundwater. And the field results demonstrated, good performance over a short period of time. I'll get into the implications of that here as I close. But within this window of the study, the demonstration did what we wanted it to do. And so saw good distribution, saw good performance in the areas that we got the carbon, and importantly, didn't have hydraulic conductivity changes within this treated area. And so, that's great. You can do this for a couple of years, but then, what are the long-term implications for treatments like this? And, that's another area where academia and working with researchers outside of what we have capabilities to do really comes into play. And so this is work that's done, again, in the group of Ein Phams lab, where they were looking at the impact absorption of the activated carbon that we use on co-occurring organics. So if you look at PFOS and PFOA and the impacts of just natural organic matter, so this is Swanee River fulvic acid, your isotherms, which are kind of drawn out by the plots here, as you increase the NOM, the Swanee River fulvic acid content, you do see a reduction in absorption. So same thing with PFOS and PFOA. And then here you can see the effect of this. This is diethylene glycol butyl ether. It's a common component of AFFF. So when this is present, when you've got organics that can compete for absorption, you do see a reduction in the absorption capacity of these in situ treatment of activated carbon. And so, this is something that's got to be accounted for and considered in the design phase if you're implementing these types of absorption retention-based strategies. Another important area that is of intense research and interest is what's the long-term effect of just putting things like this in the ground. And so this was a study that looked at what I call advanced aging processes. So wet-dry cycling, if these carbons are exposed to air, drying out and then rehydrating. Hydrogen peroxide, so this is quite a strong oxidant, or Fenton chemistry, which can, in addition to producing hydroxyl radical Fenton reactions, you can deposit iron out into the carbon pores. And so, these are the kinds of things that have to be looked at, considered when we're trying to understand, okay, great, these approaches work for a couple of years, but what's the long-term prospects of them? How long are they going to last? Am I going to be coming back every couple of years to do this? Or is this a viable long-term strategy for managing these impacts in groundwater? There's more to it. There's also hysteresis that other researchers are looking into. But you take these effects from co-contaminants from aging and layer it on some of the modeling that's been done under more ideal conditions, which this is a publication that looked at that. Some 2D modeling on lifetime of these treatments demonstrated that, for single solute species here, you can get, again, this is 2D modeling without any of the implications of the contaminants or the co-contaminants and the aging that I talked about, but you do have significant lifetime possibilities depending on a variety of factors. So, and that's what this publication that recently came out tried to kind of distill down into, for these barrier type applications, what are the major drivers for longevity? And You can see here that this tool, very simplified. We put this diagram together to like kind of offer the concepts, which I'd encourage you to check out if you're interested. This paper that has a tool for modeling or very rough of the back of the envelope, figuring out how long these barriers would work in the absence of the aging and other contaminants. But it's your groundwater flow rate, it's the PFAS concentration, the composition, and then how much of these sorbents have you put into an area. Those are really what's going to drive the longevity, in addition to those co-contaminants, the aging processes that are at play. But this starts to give you an idea. If I take this modeling and I start to layer on these real world implications, geochemistry, aging, et cetera, what's the longevity going to be? But when you take them and put them together, we've got very long potential lifetimes, but then we know that we've got things that are going to attenuate that lifetime as well. And that's part of the building the understanding of these technologies. And so just wrapping things up before I take questions, I hope I demonstrated that given how widespread PFAS impacts are in the environment, in groundwater, we're going to need a toolbox of options. And using these sorbents, using these monitored natural attenuation, and enhanced retention type approaches is a viable strategy. It's going to be a part of what gets done and saves those resource and energy intensive methods for when they're used most effectively, pump and treat and destruction methods. And collaborations through academia really help us understand how to use these tools right, when to use them. And I hope I show that it also gives practical and technical insights on both sides. So the folks that we work with and collaborate with, they get the opportunity to see, what the challenges we deal with in the field are, and we get to benefit from the advanced methods and tools that folks in academia have at their disposal. And so with that, I would be happy to take any questions, and this is how you can ask them.
Thank you so much, Paul. Let's see, can we, we're giving you a virtual clap.
Thank you.
It's always so unsatisfying in this webinar format because you can't hear all of the appreciation out here. Thank you very much for that talk. You packed a lot of very interesting information into your talk and left us sufficient time for questions. So thank you for paying attention to the time as well.
Yeah.
We've got questions pouring in. I'm going to try to organize them into categories. So there's a number of questions related to like what happens with the activated carbon in the long run? Does it just stay in place? Is it mobile? Are there conditions under which this colloidal carbon could be mobile? And then if I understand correctly, like the PFAS aren't going anywhere. They're just immobilized on the carbon. You just showed some data saying that the lifetime of the or the potential to continue adsorbing could be on the order of tens to hundreds of years. But can you just elaborate on those aspects a little bit more, sort of
Certainly.
practical aspects?
So I'll start with the retention of the carbon within the soil matrix, because that's one that comes up. It's very relevant for regulators too, because they want to know, are you just putting this contaminant on something that's going to go somewhere else and cause a problem down there? There's a lot of engineering involved to get these colloids to move in the subsurface. So we formulate this activated carbon. I didn't really touch on this, but it's in a polymeric dispersible solution. It's all kind of environmentally friendly materials. But the idea is that if you don't put something else in, formulate the carbon with something to help it transport, it doesn't go very far. So what happens is that after you inject these carbons, there's some time that the polymers and these dispersants, they wash out, they biodegrade, and then you're left with something that looks much more like that bare carbon. It stays put. And so then, if we understand our soils and we do work to try to benchmark, this much carbon will stay in place, unless you get rapid groundwater flow or just like crazy changes in the groundwater velocity, by and large, it stays there. So that's one part. Then the contaminant mass also, it stays put. We don't try, at least for now, to remove it. There have been technologies that are proposed, so smoldering or combustion techniques, for example, that if you wanted to go in and remove the contaminants later, that's a potential. But one idea is that similar to this PFAS enhanced retention, or these monitored natural attenuation, is similar to things like radionuclides. You're kind of accepting that they're there, they're not causing risk, they're not going somewhere else, at least at not at concentrations and at masses that you're concerned about. And so it's a trade-off to leave it in place versus take it out and do something with it. But again, it's one of the best available technologies at the moment. And was there a third part?
I think you did a great job addressing the multiple components to my question. Let's move on to one I'm sure you were probably expecting. Is Regenesis focusing on improved methods for short chain PFAS remediation, or are they not as much of a priority because of their shorter half-lives?
We're always open to ideas on how to improve this, and we've put some thought into it. There's, can you use ion exchange resins in addition to the carbon? Others have looked into this and worked in it. The real answer for the moment lies in the lack of regulation, and quite frankly, the data that I showed on this AFFF impacted site, you see a lot more of these lingering long chain. Not to say that the short chains aren't there, because I showed you data where PFBA is present. It's difficult. We'd love to come up with solutions. We do put some thought into it, but at the same time, the regulations aren't driving us there just yet.
Another question, have you considered using other sorbents like Fluorosorb? And the question is phrased, into a permeable reactive barrier, or GAC, and how does that compare to the injection of colloidal carbons?
That's a great question. Those are also strategies that folks are using. So using Fluorosorb, you can still do all sorts of things with resins or other materials like this. So you can build funnel and gate type approaches where if you've got the right location, you've got the ability to come back and do removals of your material. There's lots of research that's going on right now into both those other materials that you state. The preference for colloidal carbon is that you're able to leave it in place, and it's not as intensive in terms of the infrastructure that you either have to bring on site to put the project in the ground, so you don't have to excavate and generate soils and then trench in things that are like granular activated carbon. You can't inject that. You can't evenly distribute that. So that's the strategy with colloidal carbon. Again, different sites are going to have different tools that people reach for, and this is one approach. This is what we offer basically. Those can work too.
And have you considered performing any type of pre-treatment, like further up in the plume, to remove the constituents that interfere with absorption, like reduce the absorption capacity of the PFAS on the colloidal carbon?
That's a great question. So one sort of ideal site type that we can get our hands around are these hexchrome impacted sites. So hexchrome platers use PFOS oftentimes as a mist-suppressant. And so you find a lot of these commingled plumes where you've got hexavalent chromium and you've got PFAS, and oftentimes you also have chlorinated solvents. And so we've now done a few remediation works where you put in iron upgrading. So zero valent iron is able to break down the TCE that may be present, immobilize your chromium, and then that's then lowering the capacity on what hits the carbon. Hexavalent chromium doesn't really absorb onto activated carbon at the pHs that we work at, but the example is that you can use things like iron or other strategies to try to deal with the contaminants upgrading. There are other potentials as well. One thing is that if, for example, like landfill sites where you got PFAS, the TOC is just too high. So unless you're going to do something like source removal for these situations where you've got too much gross other contaminations, this method, these sorbent-based methods aren't for everywhere, but we do have strategies when possible to deal with co-contaminants like the hexavalent TCE situation.
Wonderful. So we are about at time. There are some really great questions and comments still in the Q&A panel, and also some nice comments in the chat. And so I want to emphasize that Paul and team at Regenesis will plan to respond to any questions that we didn't get to in writing after we conclude today. So you can expect to get follow-up from them if, mediated through AWSP, if you are here today and your questions did not get addressed. I want to thank everyone for being such an engaged audience. I want to thank Erica Marin and Kendall Soto at Stone Harbor for supporting us and being able to organize and offer the webinar and have such a smooth experience with our Zoom platform. And I want to sincerely thank Dr. Paul Erickson for an excellent talk and for kicking off this new webinar series with our sustaining members. Thank you so much, everyone.
Thank you, Cara. Look forward to tuning into some of the other webinars.
Yes, and on that note, we have our next webinar will be on October 9th with OLI systems and on thermodynamic modeling. So please sign up for that one as well, and we'll see you again in a few weeks. All right, we're all done. Enjoy the rest of your day or evening, everyone.